Okay, next topic is gradient fields. And we're going to spend a lot of time trying to determine if a given vector field is a gradient vector field. So this is a definition for us. And the reason it's going to be so important is down the line, we're going to connect gradient vector fields to something called conservative vector fields. Conservative vector fields are so important because they make computing those things I mentioned last time, work intervals, particularly easy. So first of all, we have an R2 vector field. We wonder, is this a gradient field? Okay, so I got to tell you what the definition of a gradient field is. But we could ask this question and answer it for R3, R4, Rn vector fields. But I'm just going to show you the definition now for the R2 gradient vector field. It's easy to extend it to the R3 and R4. So an R2 vector field is a gradient field if there exists some scalar function. So this was our usual z is a function of x and y. It's an explicit functional form. That was all of book 3. It's called a scalar function because the output, you input an x and a y and it outputs, instead of a vector, it outputs the scalar z. Okay, so a vector field is a gradient field if there exists some scalar function, f of x, y, which we are going to call the potential function. So those are a key vocabulary for us. If there is some potential function such that you take the gradient of that potential function and you get the vector field. Okay, well, this seems kind of funny because we have kind of done that already a lot of times. I mean, in book 3, we had a function, a little f, a potential function. We took its gradient. That gradient actually made a vector field. So there's a whole class of vector fields which could be generated from explicit functions, right? So there is that class. But here we're just saying, hey, here's a vector field that might describe some motion in something you're trying to study. Fluid flow, air, electromagnetics, magnetic fields, electrical fields. So if you have this field, we're wondering, is it a gradient field? Again, just get good at answering that, and then we'll see a couple more videos why that's so important. For now, just get good at answering, is it a vector field? So this is saying, can I work backwards and find some little f function, some explicit scalar function, little f, that when I take the gradient of that, I get this guy back. So again, we're kind of working backwards here. If we can do it, you have a gradient field. If you can't, don't have a gradient field. It's going to be that simple. And you're going to work through this section in the journal. There's some pages on gradient fields, and there's several examples of functions that are and are not gradient fields. Okay, so for this one, we'd have to come up with what we need. We need a function, a scalar function, the potential function f, such that f sub x at xy is y, and f sub y at xy is x, right? That's what we're trying to get. We're trying to come up with some scalar function called the potential function. Does there exist a potential function that the gradient of that is your vector field? So our vector field was given, so we want to say, is there some little f out there that I take the partial with respect to x, I get that first component of y, I take the partial with respect to y, I get the next component of x. So one thing you could do then is to try to work backwards. So I have this equation that represents a partial derivative. Can I undo that to get back to the function? Yeah, remember how differentiation and integration are inverse operations. One does something, one does it. So I kind of want to undo this partial, and I can do that by integrating. So I can integrate both sides of this equation with respect to x. So let's just focus on the first one here. And so that would say f of xy is xy plus, and now we have to be careful. The constant of integration is actually the most general constant of integration that we could have is, say, g is a function of y. Why does that make sense? Well, because again, check if you do the partial differentiation here of this potential function, right? And again, we're still not sure if it is. We're just trying some stuff out by working backwards. This potential function is a actual potential function if I take the derivative of this with respect to x and I get y. Okay, so I take the derivative of the first part with respect to x, I get 1. Derivative of the second part with respect to x, and I get 0. Okay, so that works so far. But this potential function, again, is a potential function. Is an actual potential function if now I take its derivative with respect to y. So f sub y of this function will be x plus derivative of this with respect to y, g prime of y. This will be an actual function if that is just x, right? So those have to match. The f sub y has to match right here. It almost is there, and it will be the case that this g prime of y is 0, so long as g of y is just a constant c. So if this is c, then this statement is true. So the actual potential function is f of x, y is xy plus c. And then again, check, is that actually a function whose gradient is the original capital F vector field? Yes, it is, because the gradient with respect to x is y, the gradient with respect to y is x. Check. Okay, and these problems are like that. You're sort of working backwards to guess, can I come up with a potential function? We could, because we could set this general g of y to a constant that made it all work out nicely. I'll do a couple more examples where we'll see these aren't, it's impossible to come up with a potential function. I can't make this g of y do what I need it to do. Okay, so again, here's the summary of this basic first example. We have an R2 vector field. We're wondering, does it get the new vocabulary of a gradient field? It does. If this condition holds, you can find a potential function, which is a scalar function. Z is a function of x and y, an explicit form, that when you take its gradient, you get the field back. Again, it seems kind of like, why are we belaboring this? Just keep trying, hang on there, and we'll explain it in a bit. Okay, I'm gonna pause the video and put up a new example. Okay, this example, the only thing I've changed is I inserted a minus sign here. Still an R2 vector field. We're wondering, is it a gradient field? It'll be a gradient field if we can find a potential function such that the derivative, the gradient of that potential function is the field, the R2 field. So we start the same way. We can sort of work backwards. We need to find a potential function f such that partial with respect to x is y, and the partial with respect to y is minus x. So we can start off the same way. It doesn't matter which one you want to start with. Let's again start with the f sub x. I want to work backwards from this and see if I can recover the f, not the partial with respect to that. So I'm going to undo that with the inverse operation of partial integration with respect to x. And I will say that I have a potential function, potential of x times y plus, again, we have to be general, g of y. The derivative of that with respect to x will be y plus 0. Okay, so that's good there. But now I need to take the partial of that with respect to y, and I'm hoping I get minus x. If I do, that potential function is an actual potential function. So I take a partial with respect to y of my potential function, and I get x plus g prime of y. So there's things you can do with the g of y to make g prime of y go away and be 0. We already did that last one, and we can set it to a constant. But there's no way that I can make, with this potential function, get a negative x here. There's nothing I can do that's going to make that happen. And so there is no potential function. There is no f that's going to give us, when you take its partials, put them in the vector, the gradient of that gives you this. So this one has no potential function, and it's not a gradient field. In fact, most gradient fields, R2, R3, and higher, are not gradient fields. It's actually kind of hard to satisfy this definition. However, in another sense, it's actually kind of easy because I could take any differentiable explicit function, z is a function of x and y, as long as it is differentiable, I can compute a gradient. That gradient actually, set your f's of x and your f's of y in R2, that is a vector field. It's a vector field that has a potential function that actually was the function that generated it, right? So it's easy to make infinitely many examples of gradient fields, but on the other hand, if you just make up an R2 vector field, just throw anything in the first component, it's like, hey, I wonder, here's a vector field, I'm gonna make one up, right? Like y squared plus x, x minus 2 plus square root of y. That's an R2 vector field. What's the chance that's a gradient field? Slim to none, right? Because I just made it up, just pulled it out of the air, made it up. If you were to work backwards and try to generate a potential function, not going to find one. This is not a gradient field. It doesn't mean it's not an interesting field, something we study, and we're going to get to that, computing the work done by this field to move particles of water through a pipe, to move a particle through the air, to measure how much work is done by a wind or a velocity vector field. We can do that analysis, but the analysis is so much easier when you do have a gradient vector field. Remember the original one, f of x, y equals y positive x. That was a gradient field. So when we have a gradient field, some of our later computations will be so much easier. Again, doesn't mean these aren't interesting. They're just going to take more work for us to do those computations on them. Okay, so you have several more examples in this section on gradient fields. Examples like this where here's a function and I work through the math of checking, can I find a potential function or not? All right, so you're going to check those out, finish those examples, the next page here. Some more about finding those potential functions, whether they exist or not, with a partial integration. And then the sort of summary of why we care. We're going to get to connecting this to something called conservative vector fields, coming soon. Okay, so next topic then is what I keep sort of hinting at is the work done by a vector field. So that'll be our next video.